Hello friends, welcome to our channel Knowledge Amplifier. So in my previous video, I have discussed about momentum based gradient descent. Okay. First we have seen gradient descent concept, what is the mathematical intuition behind this particular one, how to implement linear regression using gradient descent, all this I have discussed initially. Then we have seen that gradient descent is slower. So to make it faster, we use this particular algorithm, which is momentum based gradient descent. And I have already shown you the visualization that how much faster this momentum based gradient descent converges. Okay. But before moving ahead with new concept, I just want to rectify one thing, that in my previous video, I have shown this particular code for momentum based gradient descent. As you know, we here the updation rule is update value should be some particular parameter that is often called accelerating factor, we can say. Okay, that is gamma into previous update plus eta, which is learning rate, into the gradient. Okay, now this is for each individual independent variable you have to do. Like in my previous video, I have taken one particular function of two variable, but I have used one update method only. See, update equal to 0.9 into update plus 0.01 into 10x1 plus 4x2 minus 14. Okay, and I have used same update method for both x1 and x2. x1 equal to x1 minus update, x2 equal to x2 minus update. This particular part you have to modify. Sorry for this particular mistake. In the description box, I have also written that I have updated x1 and x2 with same value each time in the momentum based gradient descent visualization, but here it will be different depending on the partial derivative value. Okay. So that means if you check the momentum based gradient descent, this particular code, see, x1 value has to be updated with the partial derivative of the function with respect to x1, and x2 has to be updated with respect to the gradient, which we will be getting by applying partial derivative on the function with respect to x2. Okay, separate two, update 1 and update 2 will be getting, and as you know, both update 1 and update 2 initially should be assigned the value 0, because this is what we have learned in our momentum based gradient descent, and I have shown you mathematical derivation also. So like that same assumption we are taking here and we are proceeding. Okay, so keep this in mind. Now coming to today's discussion. Okay, so there is one very important advantage I have shown you in momentum based gradient descent, that it converges very fast. Okay, it takes lesser number of iterations in case of our compared to our normal gradient descent. Right now, you just recall what updation method we have used for simple gradient descent. That is nothing but next x is nothing but current x minus of eta, which is learning rate, into gradient at that particular location. Okay, gradient at current location. Now suppose in our function one horizontal type part comes. Okay, that time gradient will be 0, right, and or nearly 0. So as a result, that time our optimizer might not work and stop there. Okay, let me show you that. I am just taking one simple function x cube. Okay, well known from the mathematics concept, right? I hope you know how x cube looks like, and I am plotting from -1 to 2. So you just see that here slope is present, but suppose while iterating our code comes somewhere at this point, here this is almost horizontal. Okay, and so as a result, what is happening, that the gradient at any point in this location will be very small, near to 0. So as a result, our x value for next iteration will not be updated that much, because our formula is x equal to current x minus eta into gradient. Gradient is very less, so eta into gradient, the changing factor will very much decrease, and as a result, the algorithm will think that okay, I have reached the convergence criteria, I have reached the optimal solution. But you can see this is not local global minima is appearing here. Okay, but if you are applying momentum based gradient descent, you can just compare this particular situation with momentum, what you have studied in physics. Due to momentum, what it will try to do, it will try to move further, and as a result, there is a possibility that in iteration that point might overcome this region and can go to our global optimum point. Okay, So here is the code for visualization. I have shown 50 iteration I am doing. Initial random guess 2 I am taking. X equal to x minus of learning rate 0.01 into derivative of x cube is 3x square, right? And I am plotting that value and giving pause, right? And this one for deleting each time the figure apart from the last iteration 50. Okay, so I will be posting the code in the description box also, no need to worry, you can go and check there, right? So here is the code, the output figure window. Now if I just run, see the point is coming, and as this is normal gradient descent, so the point will think that it is not updating much, and the point will think, okay, I have reached the convergence region, okay, that is optimal solution. But same code with 50 iteration only, I am applying momentum based gradient descent here. See, nothing changed, x cube function only taken, 50 iteration only taking, just update equal to 0.79 into update plus of 0.01 into 3x square. See, here also we have updated 0.01 into 3x square. Here also we are doing the same learning rate, just I have choosing the one more hyperparameter in this particular algorithm, which is the accelerating factor is 0.79. okay, and 50 iteration only I am taking. Now if I run this particular code, you might see the change. Okay, see, now if I just run, see the ball is coming and it is much faster compared to our normal gradient descent, and see it eventually reached this particular optimal point. Okay, so it is able to overcome this particular region where it should not stop. Okay, similarly, like the same explanation you can apply to overcome the local minima. Okay, so here I have written one more code with another function to just give you the feeling of the power of momentum based gradient descent. Here I am taking x into cos pi x. Okay, so if I just run this particular code in the range of -1 to 2, let us see what we can observe. The function is looking like this. Now suppose my initial random guess is at this point. Now what will happen? Gradient descent will come down, and here it might see, okay, I have reached the optimal part, because here in this particular location one time gradient will become 0. So next x value equal to current x minus eta into gradient. So next x will be equal to current x, so that it will not proceed further, right? But what will happen with momentum based gradient descent? Due to momentum, if you choose your hyperparameters properly, that is learning rate and the corresponding accelerating factor, it might overcome this range and it might come here. Okay, let's see that. So I am taking initial random guess as 1 minus 1, 50 iteration doing, putting the derivative value. Okay, so you can just calculate the derivative using this particular symbolic toolbox. Let me just show you how to calculate. I have just run this and diff of fg. If I just run, see, cos pi x minus x pi sin pi x. Okay, this is my derivative, right? So what I am doing here, updation rule, same like gradient descent, x next x equal to current x minus of learning rate 0.1 I am taking, multiplied by my gradient at that point. Okay, x value initially I am choosing -1, then plotting the same. Run this whole code, Control A, evaluate selection. Okay, the figure window will come. I am pressing enter. See, the point came and it stops at local minima. It is not going to global minima. So our gradient descent fails here. But what will happen with momentum based gradient descent? It might happen that it due to momentum, it might overcome this local minima and reach to global minima. Okay, so sorry, same code. Here I am taking x into cos pi x, initial random guess same, learning rate same 0.1 here I am taking. See, here also learning rate I have taken 0.1. okay, this time I am choosing my accelerating hyperparameter as 0.9 into update. Okay, and updating that x equal to x minus update. Test code same. Okay, run this, Control A, evaluate selection. Okay, you will be getting this. Now observe the beauty. I will click enter. See, the ball comes in our global optimal part, do some oscillation and stops here. Okay, So let me just run this whole code once more. So this is the beauty of momentum based gradient descent. It is much faster. There is a possibility that it might overcome local minima. There is a possibility it might overcome the horizontal part. Okay, but there is a problem that it is taking some oscillation around this particular global minima. We have seen in my previous video also in the visualization part that it has some oscillations. Okay, so there is advanced technique to overcome this particular oscillation, okay, which I will be discussing in my upcoming videos. Thank you for watching.